blast practice. So I have a couple of things, but this is going to be practical. And again, trying to focus on the analysis. So let's see if everything goes right. The first thing here is that every time that we do a search, you will get a request ID. This is the first thing that you have to keep in mind. Every time you do a search in CVI, you get a request ID, an RID. Essentially, you will notice a pattern that every time we do something on a database or in a search system, everything has an ID. It is a super important idea, an accession number, a Kimberley, something. So, in fact, it's one of the typical problems that we have when working with molecular biologists, that in bioinformatics, in information science in general, everything needs to have an ID number or an ID name, some kind of code, short code that give a way to recover the same object again. Everything needs to have a name. And in molecular biology, for some reason, people put different names to the same object and the same name to different objects, so it's always a problem. You try always to think what is the ID of this. So, for example, there is an ID for the class. There is an ID for the course. We have a code for the bioinformatics course, and there's an ID for this class and things like that. So the same way when we search in BLAST, you will have an ID of the request. And the trick is that it's valid for a kind of 1.5 days. So why this is useful? Because it means that I did the search yesterday and I saved them. I mean, and this is their IDs. So if you like, I will give you, I probably will give you the link here, but if I click here, it will open a new window and it will give you, it will show the result of a search that I did yesterday. Okay. In other words, we are not going to do the search today, mainly because doing the search takes, I don't know, 5 minutes, 10 minutes, 20 minutes, and I don't want to wait for that search to happen until, I mean, to explain. So I did the search yesterday, and the results are valid today, but probably not tomorrow, okay? So yeah, okay, let's see. Then, what is the other thing? Okay, so there is a typical example that people look for Elvis, okay? Elvis can be written with amino acid, so they want to see if Elvis is somewhere. But I did my own search, and you will see. Okay, let's go with the part that is important. For now, okay, let me share this address with you. So you see, the pattern is that there is, well, you will see the URL. I'm sending the URL, and the last part is the RID, the request ID. If you open, you will see the same screen. There is a button here that you probably should click and help you, the help videos, and this is the part that you have to see, okay? Of course, I cannot teach you everything in the class, so I am just giving you the kind of the main idea, but if you want to learn everything, you have to search other things. What I mean is that the links that I give you are part of the class. The class is not limited to the thing that I say, it's also the link that I give you. Okay, you have to read the thing that I give you. Now, you see, for example, this request ID is here, and they will finish at 11, at 3 p.m. today will be finished. So just one last comment. I will send you the other links in a minute when we need them. You should, every time you do a search, my advice is write it down. Maybe copy and paste if you like. But since you will, well, there is a way to do it easier. I will show you. But the problem, as you see, is that this is not working. What I mean, this is not valid forever. The requests, the results are stored for 36 hours. If you want to use it again, you have to search again. So there is an option of save the strategy, save search. Okay, there is an option that allows you to save. When you save the search, you don't save the result. You save the question. Okay, you save the request, not the answer. So just be clear. The request ID will show you the answer and is valid for 36 hours. The search is valid forever. You will repeat it later and you will have different results because the database may change. Okay. So before we go there, there is a point. For that to work, for this save strategy, save search strategy, you must be logged to my NCBI. Okay. So here you see when I connect with my name. I create an account, and you can also create. Typically, you can just use your Gmail or maybe Facebook, I don't know. But typically, you can connect with your Gmail account. And so you use your Gmail password. You don't need to create a new password. And you will have essentially this area in the NCBI website that allows you to store these queries, this request. Okay, let's see the result. So I will show you the alignment first, maybe, just because it's a joke. So what I do always the test, I look for Andres. And I found that there is Andres. Can you see the screen? I click on alignment. So instead of looking for Elvis, I look for Andres. In fact, you can even look for Andres Aravena and you find something. Now the question is, what is the meaning of this? If there is special meaning, then you see what is the expect value. This is the first thing that you have to say. What is the meaning of this expect value? This is the kind of exam question. What is the meaning of this? I Google for Andres, and on Google I blasted for Andres in a database of protein, and I found it. What is the meaning? Am I immortal? I am like Elvis?
There are too many possibilities to...
Okay. How you know that? That is the correct answer. The question is how you know that?
I don't know.
So you say the correct answer, but you don't know why you have the correct answer. Like a lucky guess then. Is it a lucky guess or not? What is the expect value here? This is kind of the keyword here. We discussed it in the last class. It was the topic of last class, and it was the first thing that I remind you today. When we look in a database, we get a value that called the e-value. Okay, when you compare two sequences, you get a score. But when you compare many sequences, you can calculate something called an e-value and expect value. What is the expect value? This context. Did everybody wrote the number? No. Yeah. See? I don't know if the automatic recording is speaking or what. Say something.
Trial
Say something.
version.
Trial version, I see. I don't know why.
Was like
why they are.
So
threshold.
e-value.
Sorry, Arda, go Arda.
There was a threshold, and
Okay.
the values over the threshold, we say
Yes.
it's a hit.
Yes.
But I
Perfect.
don't think I understand properly the threshold.
Okay, that is exactly what we want to put here. Okay. Who else was given an idea? This is the basic idea. This is the most important thing to get about, well, not one of the most important. There are more, but this is one of the important things.
Well, e-value represents the size of the part of the database we're looking for, no? Like your expected e-value, expected value is 8,395.
Okay, here is where the words are important because phrases that seem similar have different meanings. And this is where it is important to be careful with the wording. So it's not the size of the database, it's the size of the results, the number of results that I expect to find in a database of this size, just by chance.
Oh, okay.
Just by luck. That is what I was saying. Is this like a lucky guess? Is this something meaningful, or is just by chance? What we say is that given this database size and the size of the query and so, I expect to find around 8,395 hits of at least this score. This is a score, 21.8. And I expect to have thousands of them. And I found one. So find one when I expect 1,000 is kind of, yeah. I can find one, I can find 10, I can find 1,000, I can find 8,000, and it's still not surprising. If I find 1 million, then I will be surprised because I expect 8,000. And 1 million is more than 8,000. But if I find one and I expect 8,000, I'm not surprised. It means that what I found is probably due to chance. I have like 8,000 chances of finding it by random, by good luck, and I found one. So what it means is that we don't have any argument here to say that this is biologically meaning. The fact that I found my name in the protein database doesn't mean anything about protein. It's just something that can happen by random, just by chance. Something has to happen. What is the probability that I happen just by chance? Well, very high. So it is not something that we say, oh, I say, meh. So the expect value will tell you essentially if you have to say, oh, or you say, meh. This is meh, because it's a big number. So let's see another more interesting here. I have the this is with a larger protein, and then we have the 16S of Terje. So I am also opening this one. And I will give you the same link. You can open it. Okay, this is a little more interesting. Let's go back to the summary here. Well, in fact, the slide is just telling here. I have job description, description in general. Let's see the part. By the way, there is a if you may have a different screen because there is a kind of the old page There is an old page and a new page. We will take a look, but there is some search will show you a screen that looks different but has the same information. It's just that they change from an old presentation to a new presentation. They are kind of updating the website. Okay, we will see it later, but even if they look different, the structure is the same. They have the same meaning and the same logic. Okay, so basically, here we have the login. If you log in, here you have kind of context. You can save it. The summary we're going to talk about later. And this a couple of things that I will show you in a minute, okay? But let's focus in this result. This is kind of other results. You have help that I strongly recommend you to read. And here we have, so we have this job. The job, you can put a name to them just to remind you. For example, this is Terje biofilm. The biofilm, the sequence from the biofilm that Terje gave me to examine, okay? This is just called protein sequence, is kind of not very good. So here it took a random name. We will see why. So this is the request ID and when it will finish. And I have option to download. We will see this in a minute, okay? But this is probably what you will like to use at the end. I mean, it depends on the analysis that you are going to do, but I personally use this one. Okay, this is the one I do because I want to do everything in my computer. Then, in this case, I submitted a FASTA file. In fact, I can give you the FASTA if you want. Now it's working. Yeah, this one. Something like this. So these are from a paper that we wrote with Phyllis. Phyllis Gurel. We published these papers a couple of years ago, and when she did the research, okay, she invited me when she got the data ready. So here we have this. It's a FASTA, very short names and the sequence. We're going to work with this, okay? Not only today, also next class. So keep this file at hand. The important thing is that when you get this kind of FASTA file, you should have the instinct of opening with a good text editor. It is good that you have something like Atom or Visual Studio or even Notebook or what is not Notepad or WordPad. Not with Word. Never use Word for this. It's a sinful thing to do. But you can open with Word, the WordPad or Notepad, and see what is happening here. So it's a FASTA, and they are protein, and there are 10 or 11 sequences. Okay. This is the FASTA that I searched in the BLAST thing. So here you see what were the search. You see that since I uploaded a FASTA, there are 11, with 11 queries, there are 11 answers for each one of the queries, okay? In other words, if you upload to BLAST a FASTA with several sequences, you will have several answers, okay?
What did you search for here exactly? Like you upload the FASTAs, but what are we looking for?
I'm looking for what are the closest, the best local alignment. We're doing BLAST. BLAST is doing only one thing. What is the best local alignment of these proteins in a database? What was the database? I think the database was here, RefSec protein. I want to identify this protein. I want to see which other proteins I have. Okay, maybe the question can be more general, like what is the question that we're trying to answer here? Well, the question that I would like to answer in that case is like, which other proteins we have in the database that are similar to this? These 11 proteins that I give you are something that we get experimentally in our department. Okay, we sequence the thing and we got these proteins. Then we want to see which example of a similar protein we have in public databases. So will be the first step to see what they have in common, what they have in difference, what are the functions that they do, what are the conserved parts, what are the non-conserved parts. That is a kind of question. What is conserved, what is not conserved? Kind of identification, kind of a generic evolutionary context. So the query are the sequences, and the database is RefSec protein. Okay, you can see some detail, how many inputs. So how many, this is the D that we say is how many? 181 million proteins. Okay, and it's kind of a small database. Remember, we discussed about databases previously. Okay.
Yeah.
So we are going to check, well, today let's focus on the first one. We can check the others later. Let's start here. We have the first kind of a description of all the hit that we got. When I searched, one of the options I choose was number of output. Let's see here. No, this is the one that we did before. Here, protein blast. I search it here. Okay, I am not repeating, but I search in here. I click in choose file and attach the file directly. I did this. Click, upload. Okay. I didn't need to copy and paste. Just upload the FASTA file. I put a name here. Well, or not. I choose the database here. I choose the algorithm. You are doing work on this. And I choose directly here. But let me show you something. The parameters that you have here include how many results I will get. And I say I accepted the default of 100. I can choose to have more results. There may be thousands of sequences, and I'm choosing, show me just the first 100. Okay. Essentially because I believe with 100 will be enough. There is the e-value threshold and the word size. Okay, this I wanted to show you that there is a parameter word size here. The default in this case is 6, meaning that they try to do it fast, even if they may make some mistakes. If you want to be more sensitive, you have to make it with 2. For example, for looking for my name, Andres. Okay, yeah, 6 words. They choose to start with 2. I mean, you have the risk, for example, if your sequence is very short and your word size is too big, you will not see anything. So there is a point here of choosing the correct word size. If you want to be sure that you get everything that you can find, you have to use a small word size, but it will take longer. You can click help if you like, okay? Okay, then the matrix, I also choose the default. And well, in this case, I choose all the defaults. But you can change, you know, here it is the matrix that we discussed last week. And the gap exists an extension. Remember, this is an important question, the kind of exam question. Why we have an existence and when we have an extension, what is the meaning of this? And the filter that is part of the homework. But I wanted to show you that all the discussion about word is here, all the discussion about expect threshold is here, the e-value threshold, and the matrix, and everything that we discussed in the last class and today are here. Okay. We didn't discuss about this one. Maybe it will be another homework. And
Did we talk about
yeah.
existence and extension? Because
Yeah,
I don't
gap
remember.
opening, and the gap cost has to. We call about. It was when you were saying let's have a break. We spoke about the gaps have two parts: gap opening or gap existence and gap extension. And the keyword was affine.
Okay,
Do you remember now?
Yeah. Okay.
It's important because if you see, in the case of proteins, you only have affine extension. You don't have linear cost. You always have cost with two parts. In the case of protein, in the case of DNA, you have other option, but it is important to understand how gaps work. That opening the gap is expensive, and for example, this one with 13 opening is super expensive, but once you open, it's super cheap to extend. And in the other extreme, you go something like this. It's like opening is not so expensive, but extending is more expensive. And all this will affect what you will find. Okay, then you click everything and you say search, and it takes forever and or sometime, and you will get a result like this. Okay, I am just showing what I did yesterday. And these are the first 100. Remember, I accepted the default that showed me the first 100. Okay. And what I found that the sequence that I got, it matched Daydream DHN3, which is the protein that we expected to find, but in different organism. The scientific name, common name, for example, this is corn, no? Japanese rice.
When it says DHN3 like,
Good question.
does it showing us how they're like, how close or how far away from each other?
No. No, because the likeness here is this protein. Okay, we will see that sequence. This is the name of the subject. It means that the person who put that subject in the database, they say, I am not sure what it is protein, but it looks very much like DHN3. They don't know for sure that this is the correct protein. They only know that this looks similar to DHN3 protein. Okay?
Is it correct to put them under the same name in the database? It's like a lot of confusion.
Option? Welcome to molecular biology. Molecular biology is all a big confusion. It's all like that. All molecular biology is built in this confusion. Nobody knows anything. They are all things that are similar to things that are similar to things that are similar to things. Nobody knows anything, or very few things. But the most of the things that we know that are similar to things that we have seen before, and we believe that they are the same thing, but we are not sure because it takes a lot of money and a lot of effort to test it.
But with the proteins, we know the sequences, so we don't need to say it's like this. Is it or not? It's simple because we know the sequences.
Well, if the sequences are identical, you can say it is. If they are not identical, what are they?
They are different. It's that.
Yeah. Okay. And then what is it?
Here it says it's not it, but it's kind of it.
Let's say this. Let's say that I took, I want to classify a living organism. And I got, for example, Recep, my friend here from the holodeck, he will be a representative of human. And if I find someone like Recep, I will say, oh, this is a human. And if I find anybody else, I compare to reject, and it's not identical to reject, therefore it's not human. What it is? Well, it's not human, but what it is?
Recep-like.
Sorry?
It's Recep-like.
Yeah, exactly. It's a Recep-like. That is what we say. It's someone like Recep. It's someone like Recep. It's probably doing the same thing. It's probably sharing the same properties, but it's not identical. So we cannot make sure. How we can make sure? We need to make experiments. We need to essentially see if, let's say, if this is a enzyme, we need to see if they are catalyzing the same reaction. Or if this is a structural protein, we need to see if they form the same compound. Or if this is a transcription factor, you need to see it triggering or repressing the transcription of some messenger, some gene. So yeah, the basic problem of molecular biology is that things are similar, but not equal. And this is a super complicated problem because things that are similar, they may probably do the same thing, but maybe not. Maybe not. We don't know. So we are kind of making an educated guess.
With organisms, I can understand if we don't know what class it belongs. We can say it's close to this, but it's not. That's fine. But with the proteins, I know what the hydrogen DNH3. If it's not,
How you know that?
if it, I know the sequence. If it's not that, I can give the other thing that I think it's similar another name, so there won't be a confusion.
But
I
maybe it's a
know
confusion that you want to make. Yeah, I see your point. But maybe there's a confusion that you want to make because the point is that you are working with a new organism and you are trying to find what is the gene that in this organism plays the role of DHN3. Because remember, the proteins don't exist alone, they exist in organism, and you have a different organism that will have different sequence for a protein that have the same role. They are not the same sequence. There is no such thing as DHN3 sequence. There is DHN3 in a given organism. If you go to another organism, we have a different sequence. So how you know which is which? That is the basic question.
Okay,
How you know?
I kind of understand. Yeah.
Yeah. So there is no such thing as this sequence. I mean, you are getting like platonic, like there is an ideal sequence of DHN3 and I can compare it with the ideal, but what makes a table being a table? How you know that a table is a table? All tables are different, but they are similar and they fulfill the same role. How you know that a chair is a chair? How you know that a cup is a cup? How you know if this is a cup or not a cup? They are similar, no? So yeah, it is true that there is a moment that they are not doing the same. They are similar, but whatever. But that is the basic philosophical problem. Let's say the epistemological problem of molecular biology is that things we know that they are similar, but not very much. Okay, but let's see. So there are 2 points here. This is the official name in the database because the person who did this one, which is a professional paid by the government of US to clean this in a most professional way, say, this is the best I can say. And it can become worse. You will see this is the good case, their worst case. So you have this, in this case, they are more sure, okay? So let's see. What we have here, okay, you have the organism, but and the tax ID of the organism. But let's see the part that we get. We have the score and the query coverage. Query coverage 100%, it means that 100% of the letters of the query are included in this subject. Here you have 95. Not all letters are. Let's see. Probably it will be easy if you see the graphic summary. This 100, I'm going to show you a graphical view. This one. So this is our query with 160 so letters. Okay. And here you have each one of the resulting alignment, the subject that we found, the alignment. The first one, I put the mouse and I get a name. These are in the same order that we have here. Let me switch from one another. So look, the score is 218. The rest of the scores are less than 200. And the score is going down, 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 down. You see how the score is going down? They are sorted by score. The first is the best match, and the rest of the scores are going down. Okay? Say yes, say no. Graphical summary is the same, but with a plot. The first is aligning completely and is color red, meaning that the score is over 200. The next one, don't align completely. You see they are missing some part here. And when you go down, you see that there is a partial match, and even like matching in two parts, and lower and lower. Lower score that here is reflected with the color, and also partial match. And this is the most interesting. So we will go to this in a minute. Okay. Let me briefly show what is the taxonomy result. Here is how many hits and which is the score that you got in different taxonomy. So the best hit is here. And you see all the taxonomy of the best hit. But then you get 17 hits with the best here. This is also a kind of good hit. It can be similar to corn, asparagus, ananas. So it is very clear that we are speaking about a plant, no? Yes, no?
Yes.
Okay, let's go to the real thing. Let's go to alignment. By the way, this is the taxonomy of the result, these 100 sequences, how they organize them taxonomically. Alignment. Here there is a couple of options. Let me start with the default. Let me start with the default, and then we will play with the other option later. Okay, this is the typical result that you will see. Maybe I will make it a little bigger now. So, how we read this one? First, you have the query, and there these are the letters. Oh my God, it's not showing everything. I didn't win very much. Okay. This is the query. 1 to 60, 61 to 119, and until 161. In the lower part, you have the subject, the hit in the database that we are looking here. Okay? And in the middle, you have kind of what they are telling together. If the two letters are the same, you have an M and an M, you get the letter. If the letters are different, you have a space. Okay? Because they are not agreeing here. When they are different, they are showing like a space here. And here we have a gap. And here is something interesting. There is a plus sign. So let's try to understand this. What we have here, we have a score, okay? we have an expect value, very small. Being so small, we know that this is not something happening randomly. This is probably something biologically. I mean, these are probably related. It's not something that happened by good luck. This is something meaningful statistically. And here there are a couple of numbers that I want to discuss. Identities. 148 letters are the same. Okay, that is identity. That is 91% of 162. Agree? Positives. There are 3 more positives than identity. This is something that we only have in proteins, and I want you to take a guess of what is positive here. By the way, at this plus sign, this is one positive, another positive, and another positive.
Is it the charge of amino acid? Positive change, maybe? It was a positive positively charged amino acid, and it is still positively charged.
I don't know if the amino acids are always charged, because that's something, charge is something that can change in the life of the protein, no?
And could it be a similar change, not
Exactly.
different?
Because on the
Exactly.
substitution matrices, when we replace 2 amino acid, it's still the positive.
Exactly. Perfect answer. Perfect answer. So that is what you should keep in mind. In proteins, some substitutions are not matching, but they are still positive. They are kind of okay. You are okay with changing, and this is for me the typical case. You change leucine by isoleucine, it is going to be positive. To me, it's very easy to remember, because isoleucine, what is the meaning of isoleucine? Iso means the same. So isoleucine literally means this is the same as leucine. That is the name of the protein. The name of the protein, I am the same as leucine. So leucine and isoleucine are essentially doing the same thing. Therefore, when you look, as Arda said, when you look them in the Blossom or the PAM matrix, in the substitution matrix, the score will be positive. So in the case of proteins, you have 2 questions. How many letters are identical? And the second question is, how many are identical or similar? Identical or positive? And the similar, well, it happens to be what Ames says, is it's connected to the chemical properties of the amino acid. If 2 amino acids behave similar chemically, biochemically, then they tend to have the same score, okay, or at least positive score, okay? When you replace a leucine by an isoleucine, or a valine by a methionine, something like that, then things tend to behave in the same way, therefore the scores are positive. Okay?
But we don't get the same score as identicals, right?
Exactly. They are not, I mean, the best is replacing, reject by reject. That is the best. But if we cannot replace reject by reject, we can replace with something that is similar, and we still get something positive. It's still good. Okay?
I have another question. I don't understand the difference between gap and the space here, as in, like, there's a yes, that part, query 61, there's a space and a gap. I don't understand.
Notice that there is 3 lines here. One is the query, and in the query you have 8 letters or gaps.
But
in the middle, you have spaces, but the middle is not a sequence. The middle is kind of the consensus, kind of the votation between the 2 sides.
What does the middle represent for? Like, what do you mean by quotation?
What I mean is that you want to see the big picture. What is shared between the two sequences? What they have in common? What is conserved? So this part is conserved with a positive. This part is conserved, but the one that are blank in the middle, the spaces, mean that they are not conserved. Here, this one say AT, the other say TA, not conserved.
Oh, okay.
Okay.
Now, then is when this option may be useful. Let's see. There is several things, and this is kind of a matter of taste. I wanted to show you the default because it's kind of the default, but maybe it's easier if you say, it essentially say, if they are identical, just put a dot. So here we don't have the line in the middle. We have only the query completely. And when there is a difference, you see the letter in the subject. So if they are the same, they are putting a dot. If they are different, they show the difference. And here you have one gap. Okay? There are a couple of other. Okay, let's see query anchored with letter for identities. When you can play with this, here is something that maybe will also help to understand. This is interesting because it's showing, okay, this is probably take more time to explain, but here we have kind of all the subjects together. This is the first, this is the second. Then make it a little longer here. And here they are trying to mark an insertion, so it's get kind of hard to see the big picture. Let's see something different, flat query. The thing that you have, okay, here you have a different view. This is the query, and this is trying to align to everything. If there is a dot, it means that they are the same. If there is another letter, meaning that they are different. So as you see, there are different ways to show, and you will have something that will be more clear, something that will be less clear, depending on how you do. I personally like this one. Let's take a look at the other. So the first hit, you see, it is 93% positive. It means that there are 7% of letters that are not the same, including one gap here. Okay. If we keep going down, you will see more and more differences. Let's give a minute, it loads here. Here, for example, to align our query to this subject, to this XP, blah, 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 you need to put all these gaps here and all these gaps here. And then you still have some mismatches. You have, of course, some things that are easy. Sometimes you have this, you can go to the gene that contain this protein, or you can see it in the context of the genome. And you can download this, you can download the FASTA. Here there are two options. The FASTA of the complete sequence of the subject, or only the part that aligned. And this heat table that I'm going to discuss in a minute. Okay, the others I will talk about them in a minute. Okay. One thing more. Yeah, well, this is the alignment. Okay, let me show you something else. There is a couple of ways to show this thing. You can ask for the text version. Let me show you because this is the way that I learned it. And it's the kind of the way that you get in the computer if you do it at home. Did we get something here? This one, yeah. So, in fact, I have some of them here. Be more clear, this is the sequence that I'm showing. Let me make it bigger for everybody to see. And let's set up. Okay. So you get the option of download everything like a text file. The text file will look like this. There is first a description, and then all the alignments in the format that we saw in the web. So this is kind of the basic result that you can get from the BLAST, and you can see every one of the alignment and see if you believe them or not, if they are too similar. Because maybe these are good, but there are so many differences that maybe they are not significant. In particular, maybe you know that this part of the protein is the active site, for example. And if you lose the active site, you lose the catalytic property of the protein. So you may have that thing that it can happen that you have two proteins that are very similar, but the small difference is the important part. So this BLAST result will give you a set of proteins to work with, but then to get a different final decision about the function of your protein, you really have to go to the small detail. We will talk about this in the next class, about how to conclude this. But the point is that in some cases, you need to see the detail. In fact, before going to the other, there is one case that I want to show you in particular before we go to this detail. There's only one that I want to show you. This one. So here I want to show you this particular case. I can go here and with the mouse, I choose the one that has these two parts, and I will click and will see the alignment. Let's give 1 minute that it can load. And here I want to show you this point. In this case, we have two local alignments between our query and the database. What is happening is that there is one part that is similar, then in the middle, they are not very similar, and then a second part that is also similar. So let's see what is happening here. The query, starting from position number 9, because of the subsequence, is this one. The subject is very similar, except some mismatch. So this is the position in the query, this is the position in the subject, from 9 to 95, and in the other you have from 11 to 98. There is one gap here. But then later, from 106 to 161, it is also similar. But please notice this. Here we're 9, the position 9 aligning with position 11. Here you're position 68 with 71. They're very close. 95 to 98, like 3 amino acids of difference. Okay? But the second hit, they are very apart. This is 100 and 168. There are kind of 60 letters in the subject that are not in the query. What I mean is this: if you see this, you have two results, two hits in the same subject. In the graphical version, maybe it was easy to see. Here I can go to description. and graphical summary. Graphical summary. Here, we're talking about this one. One part matches our query. The other part also matches, but there is something in between that is not in our query, but is in the subject, and it's kind of 60 letters. Nobody's saying anything. Yes, no, maybe.
So could it be a massive insertion or something? What's
Exactly.
the biological
Exactly.
meaning?
Exactly. It's exactly what you said. There is a massive insertion of deletion depending on what you see. But since this is a more distant organism, the protein has kind of two domains that are shared, and there's something in between, like 60 amino acids that are in the subject and not in the query. And my point is that in this case, you have this kind of alignment. The point that you have to keep the alignment, since it's local, you can have different local alignment in between the two sequences. Not all alignment will give you one line. Some alignment, like this is in fact here you have several. Look, this is even worse. You have one alignment here, then another here in a different position. Look, the same sequence is aligning more than one time in the subject. This is even worse because 71 to 134 in the query. Okay? And that query is in this part of the subject, but is also in this part of the subject, and is also in this part of the subject. So we have three ranges. In other words, local alignment have to be taken with caution. You have to be careful with the thing that you find, because it can happen that you get more than one local alignment, and it's hard to give them biological meaning. So getting back to the initial idea, what Turkan say, if they are very similar, you can say something. Here we can be very confident in the first one in particular, because the e-value is small, the identities are high, the positives are high, and it goes from the beginning of our protein to the end of our protein. The protein is completely covered. So the local alignment took everything. It's kind of become global. We were looking for a local alignment, and we extended until the end. So they are a very good alignment, complete alignment. But if you go down, you may have alignment that are local alignment, still valid local alignment, still statistically valid, but biologically harder to interpret, because you have like this. Look, you have is similar to a protein that is having a different function, and you have this domain in range 1, range 2, 3, 4, 5, 6, 7, 8, 9. We have 9 local alignment between our sequence and the subject. Okay, there are two more things, but I will finish with only one. Tell me.
Why are the positives are always higher than the identities?
Because identities are positives, but not all positives are identities.
So
Well,
shouldn't it be less?
No, because identities essentially mean that the two amino acids are exactly the same. Positive means that the matrix entry is positive. That is always true when they are the same, but there are some positives that are not identical. So
Okay, okay,
the
okay, I got it. I got it.
identical is a subset of positive. So in many cases, you look at positive, but it is also good to know, for example, look here, the positives are good, but identities are essentially the same. So you are very happy here. Positive is normally good enough because it kind of suggests that the chemical properties are the same. Okay, one more thing and we finish here. There is another download all that we use a lot. I am going to skip this one for now. This is heat table text. This is the one that I mostly use and I want to show you now. It came down here. It's download the file and I'm opening if I can. Yes. Again, it looks like this. No. Yeah, no. It looks like this. In most of the cases, I am happy with this result. This is a data frame. This is something that you can load with R or with Excel. You can even load with Excel. And maybe, well, if you are careful enough, it works well with Excel. The lines that start with hash are comments, okay? And that is easy to handle. You can essentially skip them. In R, you have an option to say ignore the lines started with hash. And then you have, I don't know, 10, 11 columns. And here is the explanation. Here, the first is the name of the query. Then accession version of the, sorry, query accession version. Then subject accession version. In other words, ID of the query, ID of the subject. Percentage of identity, length of the alignment, number of mismatch, number of gap openings, number of gap, and query start, query end, subject start, subject end, e-value, score, and number of percentage of positives. Okay. If you don't need to see the alignment, this is much faster to calculate because you see this, all these scores are this is something that you calculate without doing the backtracking. You make the matrix, calculate the score, and give you the result. To show you the other result, to show you what was the other result? To show you this one, you need to do the backtracking to know where to put the gaps, okay, the positions of the gaps. In the example that I just showed you, where is this one? In this one, you know how many gaps, but you don't need to know where they are. So in many cases, this is the table. And I will tell you, in my work, most of the time I work with this table. It is shorter, it is easy to analyze, it's a data frame. And at least it allows me to identify which is the one that I want to see. And then if I want to see the alignment, I do the alignment only for the one that I see, or the top 10, top 3, or something like that. There are more things that we can see, but we are on time now. So let's get the final question. Remember, this is the point here, download heat table. There are other formats that we can discuss later, but this is the one that I recommend for working in the computer. If you want to download and see what happened and put into Excel or R or whatever. Okay?
I have one more question. Did you decide how you will make the exam? Like,
yes,
you will
I had to
upload.
decide. I had to decide yesterday, and I say homework. And I already give you one part of the homework, which is the topic that you have to read and write something. I am asking you to write, I don't know, 500 words. I want to encourage you to write a little bit because it will be good for everybody. I always regret not asking people to write. and I will give you feedback about the English that you get and of the content, of course. Because what we are going to do after the exam, we are going to give the summary to everybody so everybody learn from everybody. And we will work together on that thing. But then I will give you, my idea anyway is to try to make an exam that is short. Kind of the long part, you already got it. This is the long part. I want to, let me see. I want to have an exam like typical exam, like 90 minutes, but I find that 90 minutes is too short. So I say I will give you homework. I hope you don't take more than 1 day doing the rest of the exam, okay? So the exam, let's say, has 3 questions. I already give you question 1. Maybe, I don't know if we'll have 2 or 3 questions, but you already got question 1. So you can already work on that. And the other one should be relatively short. I give you enough time so you don't need to do it in a hurry. Remember, never about running. Okay. What I have in mind is kind of giving a result like this and ask you a question about, like giving this blast result and giving you maybe also some like how to search for sequence in the database. The first part, something like that. That is what I have in mind. Okay.
Okay, thank you.
Any other question? Shall I move my hand? Like?
I have a question.
Go
I
ahead.
wonder how we determine the cost of the existence and extension gaps. Because it affects the score.
Yes. Okay. I don't have, and I don't know if anybody got a very good answer, because I mean, if there is an easy answer, then it will be automatic. Everything that is not automatic is something that you have to think about it. If there is an easy rule, the computer already has it. Everything that can be automatic is already done. So so far, I can essentially tell you that you have to think about how much distance you think that the sequence should be. Like, if you want to be very strict, you have to make gaps very expensive. If you want to be more loose, like your sequence are very distant evolutionary, phylogenetically distant, then you have to be more tolerant. But I promise that after the midterm and after we finish kind of this part, I will give you more detail. The point is this: to give you a better answer, we need to do more mathematics, and I try to delay the mathematics to the end of the course. I want. What are the big picture here? We spoke about how to get things from the database. We spoke about taxonomy, which is connected to download things, but also to classifying things. We spoke about alignment. We have seen BLAST. Next class, we should be speaking about multiple alignment. The following, maybe in the same class or the following, we are speaking about phylogenetic trees. After the midterm, we should speak about genome assembly and how to understand the genome assembly. And then we will kind of finish all the things that you should know. And then if we have time, we will get into the mathematical detail that will give you some tools to decide which is the best gap or the gap that will more reflect the problem that you are working. That is my plan. Fine? Because unfortunately, the answer requires some mathematics that you don't have yet, but you will.